smartphone processor is smaller than your fingernail, yet it holds billions of switches flipping on and off, faster than you can blink. A stick of RAM is just gray plastic and metal pins. But inside, it's storing and forgetting information billions of times a second. A graphics card can paint 8 million pixels 30 times every second, somehow without ever mixing up a single one. A camera sensor is thinner than a sheet of paper, yet it can capture more detail than the human eye. That level of precision shouldn't be possible. 4 completely different devices, 4 completely different jobs, and yet they all begin in the exact same place. So how do factories turn raw sand into devices that think, remember, render, and see, with a margin of error smaller than a single atom, every single time? Let's step inside and find out. This chip is the brain of your phone. It's smaller than a postage stamp, but it holds more switches than there are stars in the Milky Way, and every single one has to work perfectly. It starts as sand. Ordinary silica sand is melted down and purified until it's 99.9999999% pure silicon, pure enough that a single stray atom of the wrong element could ruin the entire chip. This purified silicon is grown into a cylindrical crystal by dipping a small seed crystal into a vat of molten silicon and slowly pulling it upward while rotating it, a process that can take days to form a single ingot several feet long. The ingot is cooled slowly under carefully controlled conditions so its atomic structure lines up in one continuous, unbroken pattern. Then it's sliced into wafers thinner than a human hair using a diamond-coated wire saw. Each wafer is coated in a light-sensitive chemical, then exposed to ultraviolet light through a stencil-like mask, carving circuit patterns onto the surface. This step, called photolithography, happens in a clean room 1,000 times cleaner than a hospital operating room, where a single dust particle floating through the air could destroy a chip before it's even finished. The pattern is etched using charged gas, then layered with metal wiring only a few atoms wide. This process repeats, expose, etch, layer, sometimes over 500 times, building the chip upward like a microscopic skyscraper, one invisible floor at a time, with each new layer connecting to the ones below it through channels narrower than a strand of DNA. The machines performing this exposure step are among the most precise devices ever built by humans, using lenses so exact that if one were scaled up to the size of Germany, its tallest imperfection would still be smaller than a millimeter. Finally, the wafer is sliced into hundreds of individual chips, each one tested under intense heat, cold, and voltage stress before it's allowed to leave the factory, put through cycles that simulate years of daily use compressed into just a few hours. A single misaligned layer, by less than the width of a virus, can make an entire chip unusable. Out of every wafer produced, only a fraction of the chips will pass every test, and the rest are quietly discarded before they ever reach a store shelf. Engineers call this the yield rate, and even a 1% improvement can save a factory millions of dollars, because every wasted chip represents weeks of processing time and thousands of precise steps that all had to go right in a row. To keep that yield as high as possible, robotic arms move each wafer between machines without a human hand ever touching the surface, since even the natural oils from a fingertip could disrupt the pattern being etched. From a handful of sand to a chip capable of billions of calculations per second, this is the part of your phone doing all the thinking, and it started as dirt. A stick of RAM looks almost boring by comparison, until you realize it forgets everything on purpose. RAM doesn't store your files permanently, it's designed to forget, and that's exactly what makes your computer fast. Like the processor, it begins with a silicon wafer. But instead of building a single complex brain, manufacturers etch millions of identical tiny units, called memory cells, across the surface, each one just a microscopic capacitor and a switch, repeated over and over with no variation at all. Unlike a processor, where every section of the chip does something different, a memory chip is deliberately monotonous, because uniformity, not complexity, is what makes it reliable at this scale. Each memory cell stores a single bit of information as an electrical charge. Charged means 1, uncharged means 0. But these capacitors leak charge within milliseconds, so a controller sweeps across the entire chip thousands of times per second, recharging every cell before it forgets what it was holding. The wafer goes through the same lithography and etching stages as a processor, but instead of variety, it's about repetition, the same tiny pattern stamped millions of times with zero deviation allowed. After etching, the wafer is diced, and each individual chip is mounted onto a circuit board alongside 7 or 8 identical chips to form a single stick of memory. Every stick of RAM in your computer is being electrically refreshed, cell by cell, thousands of times every second. And if that refresh ever stops, even for a fraction of a second, everything it's holding vanishes instantly, no trace left behind. This is why RAM is called volatile memory, unlike the storage drive sitting next to it, which holds information even with the power switched off. The trade-off is speed. Because RAM never has to search through long-term storage, it can hand information to the processor almost instantly, which is exactly why opening a program you've already used once feels faster the second time. A component built entirely around controlled forgetting, refreshed constantly so your computer never even notices, all housed inside a strip of plastic and gold-plated pins. A graphics card doesn't just do one thing billions of times, it does millions of things all at once. A processor thinks one thought very fast. A graphics chip thinks thousands of thoughts at the exact same moment, and that difference is why your screen never lags behind your mouse. Like its cousins, the GPU begins as a silicon wafer, but its internal design is fundamentally different. Instead of a few powerful cores, engineers pack thousands of small, simple cores onto the very same chip, trading raw individual power for sheer numbers working in unison. A processor core might be compared to a brilliant specialist solving one hard problem at a time, while each graphics core is more like a single worker on an assembly line, simple on its own, but devastatingly effective when thousands of them work side by side on the same task. The wafer goes through the same cleanroom lithography process, layering circuits that form thousands of parallel processing cores rather than a handful of complex ones. Once etched, the chip is bonded to a substrate and connected to high-speed memory chips sitting just millimeters away, close enough that data can travel between them in a fraction of a nanosecond. The finished chip is mounted onto a circuit board, paired with a cooling system, because packing that much processing power into one space generates intense heat, and some high-end chips can reach the temperature of a stovetop burner under full load, hot enough to warp plastic nearby. While your processor might handle a handful of tasks in careful sequence, a modern graphics chip can process over 10,000 calculations simultaneously, recalculating the color of every pixel on your screen dozens of times per second without a single one ever falling out of sync. Every one of those thousands of cores has to receive its instructions, complete its calculation, and report back in perfect timing with all the others. Like an orchestra where every musician has to hit the same note at the same instant, thousands of times a second without a conductor. From bare silicon to a chip capable of rendering entire virtual worlds in real time, built not to be fast at one thing, but fast at everything all at once. A camera sensor doesn't calculate anything. It just has to catch light perfectly every single time. Your phone's camera sensor is thinner than a sheet of paper, but it's covered in millions of microscopic light traps, and each one has to catch photons perfectly, whether you're standing in complete darkness or blinding sunlight. Once again, it starts with silicon, but instead of etching logic circuits, manufacturers create a grid of millions of tiny photodiodes, light-sensitive wells that convert incoming photons into electrical signals the phone can actually use. Each well works like a microscopic bucket catching rain. The more light that falls into it, the stronger the signal it produces, and the sensor's job is to measure exactly how full every single bucket became in the fraction of a second the shutter was open. Each photodiode is layered with a microscopic colored filter, red, green, or blue, arranged in a repeating pattern across the entire sensor, so each individual well only registers one color of light at a time. Above that, a layer of microscopic lenses, each one smaller than a grain of pollen, is added to bend and funnel light directly into each well, since even a slight misalignment would let light leak into the wrong pixel and quietly ruin the image. The finished sensor is tested under both total darkness and blinding light to make sure every single well responds identically, with zero exceptions. A modern phone camera sensor can contain over 100 million of these light-catching wells, each one smaller than a red blood cell, and if even a handful malfunction, you'll see permanent dead pixels in every single photo you ever take from that point forward. Once a sensor passes inspection, it's bonded to a support chip that reads out all 100 million wells at once, converts the pattern of light and color into digital information, and hands that data off to the phone's processor in a fraction of a second, all before you've even finished pressing the shutter button. From raw silicon to a sensor capable of freezing a moment in perfect color and detail, built at a scale where the components are measured in millionths of a millimeter, smaller than anything the eye could ever hope to see unaided. 4 chips, 4 completely different jobs, and yet every one of them starts the exact same way, as a small handful of ordinary sand. It's only in the details, the pattern etched onto the wafer, the arrangement of the cores, the placement of a single lens over a single well, that sand becomes something capable of thought, memory, imagery, and sight. That's how a processor, a memory chip, a graphics card, and a camera sensor all go from ordinary sand to devices that think, remember, render, and see. Precision, scale, and engineering most of us never think about.